have an up-to-date Java certificate or whatever. Used an old version of Java, but I figured out how to get around that. Probably cause trouble. All right, so this is where we left off. Some period and frequency. The period of a wave, you could think of it a couple different ways. It's the amount of time it takes for a wave to go by. So if you're standing at the ocean and this is you, and you have some waves coming in like this, and you're getting splashed here, and then 3 seconds later you get splashed again, and 3 seconds later you get splashed again by all these waves that are coming in, then the period of the wave is 3 seconds. It's the amount of time it takes for a full wave to pass. Another short, succinct way to describe that is seconds per wave. So if every 3 seconds one wave passes by you, then there are 3 seconds per wave. So the time, writing that in the wrong place. Time for one full wavelength to pass, or seconds per wave. And frequency is just the opposite of that. Frequency with anything is how often something happens, whereas period is sort of the amount of time it takes for something to happen. So they're inverses of one another. The longer the time for one full wavelength to go by, the fewer waves you're going to see. If the waves look like this would be maybe low frequency. If the waves were like this, you would get splash, 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 splash very fast. That would be high frequency. So the frequency is the number of waves per second. Passing per second. Or each second. And the symbols for these, period is a big capital T. I suspect that's because period is just time. And little t is already time, so that's a good thing to call it. And frequency, the symbol for this, we'll get to it down here, but I'll just cross that out, put it here, is an F. The units for frequency, those are, I'll do it like this. 1 cycle per second equals 1 hertz, Hertz. And the abbreviation for that I'll be using most of the time is 1Hz. So the variable that you use in a formula for frequency is F, but then the units are Hz. And it gets kind of confusing because a hertz is really a 1 over seconds. And if you're wanting to get your units to cancel out, think of it as 1 over a second. You can plug that in and then units will work out right. Okay. So this is a little test. Period of the waves below. And I say waves because it's more than one wavelength. What would the period of that be? In other words, if somebody's standing over here and these waves, these crests are hitting them, how long is it going to take for between being hit? 0.5 seconds. Another way to do it is to start here, proceed one wavelength through one full cycle and go to there. One wavelength is 0.5 seconds, so it's 0.5 seconds. Anybody see the problem here? There's a problem. What did I do wrong? I need to fix something.
It's not the sign for
Yeah, that's the sign for wavelength. So this should be F equals. I don't know why I did that. So what if the number of seconds per wave is 0.5 seconds, then what's the frequency, which would be waves per second? 2. In this 1 second period, you get one wavelength, another wavelength, so the frequency is 2 hertz, 2 waves per second. You could do it that way, or you can just use the formula, which is frequency equals 1 over period. Alternatively, period equals 1 over frequency. They're the reciprocals of one another. So in this case, if I want to know the frequency, I can just plug in 1 divided by the period, and that gives me 2 hertz. And that's that. Any questions about that? You're going to be on the assignment practicing doing that kind of stuff. All right. Now, I like beats. Last class I was disappointed that we didn't get to beats. Constructive interference and destructive interference. The idea of interference can apply to sound, it can apply to light. With sound, what you get is extra loud sounds and quieter sounds, and you might get sounds of different pitches. Interference means waves being added together, producing some kind of effect. With light, you can have light waves interfering to cancel one another out, or you can have different colors being produced. But in these two cases, here's an example of 2 waves being added together, giving you this. And if I were to add some numbers here just to show what's going on, I'm just going to make this, let's call this a positive 1. Don't even worry about what the units are. And this amplitude is a 1 also. And if you add a 1 and a 1, you get a 2. So this is those two things put together. Right here, that's 0, that's 0. When you add that part together, you get 0. Here, this is negative 2. Negative 2, you add that, or sorry, negative 1, you add that together, you get negative 2. So this is what's called constructive interference. This is, if I understand it correctly, I think I do, this is kind of how lasers work. You have a ray of light and another one, and they're in sync with one another, and the power of them, the amplitude gets added, and you get something that's more powerful. This doesn't have a different frequency. If you were standing here being hit by these waves, ooh, you're kind of a strange build. But if the waves are moving to the right, they're hitting this person, you're going to get a splash and another splash. It would be just like this process over on the left, except the splashes would be stronger. They wouldn't be in the left. The wavelength is the same, the frequency is the same, the period's the same, but what's different is the amplitude, the strength of the thing. Now here, you've got a positive 1 and a negative 1, and if you add those together, you get 0. So this is, if you had 2 sound waves that you put together like this, what you would hear is what? Nothing. And if these were rays of light, if this was green light, and this was also green light, and these things were just slightly out of step with one another, what kind of light would you see? So green light, what kind of light is this?
Red.
No light. They're just, that would be black. If you were in a place with no light sources except for 2 little sources of green light that were like this, and they were out of step with one another, and one was going up when the other was going down, you wouldn't have any light at all. If you could get them working with one another, lined up, what you would get is still green light, but it would be more intense than before. But if they're out of step, they'd be fighting one another. And that is the essence, and I'll put this close so this thing can hear, the essence of what's going on with beats. I was doing this at the end of class last time. That's something else. I kind of want to move it. All right. I adjusted this so these are really close together, so we're not going to hear much in the way of beats. Let me mess it up a little bit, and then we'll hear more. Those are beats, and what we're getting thing with beats is both constructive interference and destructive. When there's constructive, they're adding together. And when there's destructive, they're canceling each other out. So the loud parts, when you hear it get louder, that's when they're in step. They're going together. And when the quiet part, that's when they're out of step. They're doing different things. And I can make the beats faster or slower by, now the beats are really fast. And if I screw these up enough, the beats get so fast, you can still hear them, but at some point it's hard to hear them because they're so far. Can't hear it as well. And if you're trying to tune one of these, sometimes people tune instruments by trying to get rid of the beats. Ooh, this is a really long beat. Could you hear it get loud and quiet? Now, to explain this a little better than I can just explain it in words, I was thinking today, back before I had the internet and a projector, I would just have to say, okay, picture this. Everybody imagine. I'm so glad I don't have to do that anymore. This guy. Okay. Oh, you're not seeing anything. This is two. These are transverse waves, but they're representing sound waves. And this is one sound. This is another sound. This, just by looking at it, can you tell which one has a higher pitch? Can you tell which one has a higher frequency? Is it Y1 or Y2? It's 2. And it's really hard to tell, but these are slightly closer together. Those are slightly farther apart. So it's kind of like two people are walking together. Person one is taking slightly bigger steps and stepping less often. Person two is taking slightly smaller steps and stepping a little bit more often. And as a result, sometimes they're completely out of step like this. But if we wait a little while, they get to the point where they start to get in sync with one another. And now they're out of sync again because this person's taking steps that are a little bit faster. And this is the result. This is what you get when you add the two waves together. I'm going to stop it at a good time. Let's see. Right there. So at this point, this represents the compression. If this is a sound wave, this is compression. So how compressed the air is and how compressed the air is. And what you get when you add these two together is you get extra compressed air. If this value is a 3, I'm just making that up, and this is a 3, then this becomes a 6. And I let them keep going a little while. When they get out of step with one another, right here, this one is +2, and this one's -2. When you add that up, you get 0. So when you play these two together, you don't hear this and hear this, you hear the sum of the two. And you hear whoa, whoa, like that. What's kind of strange, hard to wrap your mind around, is what happens when I start to mess with these numbers. Right now, this is 550 hertz, so 550 of these waves per second. This is 500. If I make that difference bigger, so it's kind of like, I'm going to take the person who is stepping faster, and I'm going to make them step even faster. I'm going to jump this up to 700 hertz. Are we going to see more beats or fewer beats? There's a bigger difference between them. And ultimately, it doesn't really matter. What do you think? More? So right now, in this picture, you can kind of see this is one beat, another beat, another beat. So there are 3 beats showing in this. And each beat represents a time when they got out of sync and they got back in sync. So what you get is you get more beats. There's a beat, 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 lots of them here. And it's because if somebody's going and the other person's going like this, they're just gonna, the person who's slow is gonna pass them up and then get back in sync and pass them up. That's not really that important. What is important though is just to understand that if you look at any point along here, what's happening is this is being added to that to get this. So if you want to find out a place where there is a beat, you look for a spot where this is high at the same time that is. So if I follow along right here, let's see, right here, looks like there's going to be a beat because this is going up when that's going up. Right here, not a beat. That's going to be a node because this is down when that's up. A node is a place where nothing's really happening. So on that paper of yours, see if you can do this. Hopefully you can do this now. There's channel 1, channel 2. Those are different input sounds. This is a sound. This is a sound. And then this is the product, the sum of the 2 sounds. First question says, label the one with the higher frequency. In fact, just see if you can do all these dots. Label the one with the higher frequency. Label the regions of constructive and destructive interference. Use a C or a D. And then label the beats that you'll hear in this one. So number 3, this is where you label the beats. And then put a C or a D in there where there's constructive interference and destructive interference. We'll go over that. Anybody want a crusty marshmallow? If you just get really hungry and you want a crusty marshmallow, we're here for you. Clarissa get it? No?
I have one.
You already have one?
Oh,
yeah, what? Ow, you shocked me. Yes.
It's, I don't think it's really that bad.
It takes like 5 hours.
Okay. Which of those channels, channel 1 or channel 2, which one has the higher frequency? Channel 1, got the highest frequency. It's, if you think of somebody shaking a string, they're shaking the string more rapidly. There are more waves per second there. So this is the higher frequency. And this is the lower frequency. If you're going to have beats, you've got to have 2 different frequencies to make the beats occur. And this is a very specific term. Beats doesn't always mean hearing the when you add 2 sounds together. The beat of a song, totally different than that. It's just the rhythm. So label the regions of constructive and destructive interference. This would, right in here, is this constructive or destructive? Constructive. And right here, destructive, constructive, destructive, constructive. Anywhere the sum of these gets bigger, it's constructive. Wherever the sum gets smaller, it's destructive. And without being shown number 3, you could deduce that from up here. Whether this is going up at the same time that's going up, that's constructive. Now this is going up when this is going down, so they're going to destroy one another. And last class I started thinking maybe they didn't know what I meant. Just the word construct means to build. I guess destructive is right in there. And then this is constructive again because they're going in the same directions. Then it gets destructive right here and it starts to become constructive there. And the beats, this is a beat. And this is a beat. And so is that. A beat is just the constructive interference part. This is jumping ahead, but on the same topic. Maybe we can do this kind of out of order. There's an idea called standing waves. Do you remember when Charlotte and I we were shaking this slinky, and instead of the waves going through the slinky like that, they were just going like that, kind of standing in place. Those are called standing waves, and I've got some videos of those. Here's a. See what this. If this is the one. This isn't really a. Oh, I do that every time. These are standing waves in strings. This isn't a very good video. They generate them by attaching a string to something that vibrates up and down.
Wave on his plate.
And with the standing wave, you get things called nodes. That's a node. And then over here, this is an antinode. And by vibrating this back and forth at the right rate, you can make different numbers of standing waves in there. And this is pretty long. I'm going to jump forward. Hopefully they will change the number of standing waves that we're seeing. That's still 2, or actually 1 wave length, but 2 antinodes. There you go. So now there's 2 nodes. Actually, 1, 2, 3, 4 nodes. The ends are nodes, and then 3 antinodes here. And maybe they'll speed it up some more and get some more of these. The way these standing waves actually develop is kind of mind-boggling. It's pretty easy to make them happen, but when I show you how what creates them, now we've got 4 antinodes trying to form, and 1, 2, 3, 4, 5 nodes. It's kind of mind-blowing. So watch this. This is another one of those Java applets. That's the Doppler effect. Let me get away from that. I'm going to start it. Try to figure out what's happening here. So imagine that somebody's tied a string to the wall, and they start out. They're going like this on this end. If this is a sound wave, it's going to get to the wall, and then what's it going to do? Echo. It's going to reflect back, and when it reflects back, the reflecting wave is going to interfere with this wave. So somebody keeps doing this, and from the other end, they're getting a wave coming back. And as those 2 waves interfere with one another, you get constructive interference and destructive interference. Yeah. Let me turn the lights off. Well, no, I'm going to leave the lights on because I'm going to mess up the camera. But the blue, that's the reflected wave. It's coming back. And remember when Charlotte was making waves and I was making waves? Yeah. I could send waves one way, and at the same time, she could send waves the other. They would just travel through one another. And they would do strange things. So red is the wave coming from the left. Blue is the wave coming from the right. Black is what you actually see when you look at this slinky or this rope or whatever it is. So the black is what the thing is really doing. And it's the sum of the red and the blue. So focus on this point where my finger is right now. And notice how the value of this, the position of this string, is going way up and way down. And that's because the red and the blue are being added together there. I'm going to pause it right there. So right now, I don't know if this is where I was pointing, but right now this red is at its maximum, and so is the blue, so the sum of these is really high. At this point, I didn't quite stop it right, but the red right here is at rest position, and so is the blue pretty much. So the sum of them is not very big. If I let it go a little farther, when they line up perfectly again in a negative direction, the sum of them is very negative. So in that video that we were just watching, did I have to click off of that? Yeah. Those standing waves that you see right here, this part, that I should go back to an earlier part. That blur, it looks like a blur because it's going super fast, just like that black line was in the simulation. And right here, this is just a place where, because of the way, because of the nature of the waves and the way that they're running into one another in the particular wavelengths, they are canceling one another out there. So if I were to run this really fast and get rid of the individual waves, what you would see in this area is a big curvy blur. And here you would see another big curvy blur, and right here there would be nothing. It would look like this. Now, this gets really cool if you try to do this, think about this in 3 dimensions. Get rid of that because I think I've got too many things going on. I won't ever ask you to draw a diagram to explain what's going on in this video. Have you ever seen patterns in salt made by this process? Okay. This is pretty cool. They're going to, they've got a board, some kind of a special board, and underneath that there's a speaker, and they're going to play a tone, and the tone starts waves in this board. And it's just like those waves we were looking at, where there are places where they go really wide, and then there are skinny places where there's no vibration, and those are the nodes. And what happens is, instead of one line that's going like this is happening in all directions. So wherever there's a node, that's where the salt goes. Wherever the board is bouncing up and down, an antinode, the salt pushes away. And you'll see how the pattern changes in this as they ratchet up as they ratchet up the frequency.
It's a vibrating board.
Vibrating board, and it's being vibrated by the frequency of the sound. As the sound gets higher, the board's shaking faster, and the source of the sound is in the center, so these waves are going out in all directions.
What is the node thing?
The node, I'll just leave that there so I can come back to it. Let me actually type in just so you get a picture. Standing